morning and welcome to the fourth episode of Exchanges on Exchangers. I am Christy Smith.
And I'm Cosimo Pecchioli.
And today we will talk about the evolution of data centers with two great guests. Dale Sartor, he's a staff engineer at Lawrence Berkeley National Laboratory, and Bruce Myatt, data center business leader at ARUP.
Bruce, if you want to introduce yourself.
Well, thank you. Yeah, my name is Bruce Myatt. I am the data center leader at ARUP in the San Francisco office. We are a large global design firm that designs many types of buildings and many types of infrastructure, from the Sydney Symphony House to some of the great bridges of Hong Kong and around the world. And we've got an extraordinary data center design practice as well. We're headquartered in London, England, and have about 25 offices around the world that deliver data center design services, hyperscale, co-location, and enterprise and government data center operators. I personally have been in the data center industry for about 20 years, worked for some of the other large data center design firms in the country here in the United States, and helped develop a group of end users called the Critical Facilities Roundtable about, my goodness, it's been over 15 years ago, and Dale was very engaged with that. And
I was just barely out of college then.
Yeah, sure. But anyway, we've had a real interesting run of driving new technologies, and encouraging people to learn about them and adopt them in their data centers, and appreciate everybody who's made those contributions to this industry around here in Silicon Valley.
Thank you, Bruce. And Dale, do you want to introduce yourself?
Sure. I'm Dale Sartor. I'm a staff engineer at the Lawrence Berkeley Lab. My focus is in the area of high energy efficiency for buildings for the high-tech industry. And probably over the last 20 years, that's focused on data centers. So data center energy efficiency is what I work on. And we do a combination of R&D, but also a lot of market transformation and deployment programs working throughout the world.
So Dale, let's start with you, and not to divulge your age, but you have been in the business for quite a while, and there's a lot of young people that are in this market. I mean, maybe you are not very familiar, that they are not very familiar with the challenges of the industry. So I was wondering whether you can maybe take a walk with us in the memory lane and explain about the cooling challenges that you have seen and the evolution in the data centers.
Sure. Well, the first data centers were liquid cooled, and that was even before my day. But for that reason, the old timers in the industry are not as concerned about liquid in their data centers as some of our younger colleagues are. As the data center power density is increasing, it's making it increasingly difficult for air cooling to meet the demand. So liquid cooling is a much better heat transfer medium, and for a variety of reasons. And as our data centers become more power dense, there's a move back to liquid cooling. Liquid cooling offers significant energy and water savings opportunities. And typically, the closer the liquid gets to the heat source, the more efficient the system becomes. So starting with the CRAW unit, that's using chilled water usually, and it's probably the least efficient, moving to in-row cooling, then rear door cooling, then cold plate, and then immersion. Typically, you're going to get slight improvements with each one of those steps.
So, and that's fantastic. We were talking about specifically about liquid cooling, but let's say I probably the liquid cooling has been around for a while, but now it's emerging like something that is they will become probably kind of mainstream. But I would say probably 15, 20 years ago, it was not even kind of existing, except at the real beginning, as you said, at the dawn of the data centers area. So why do you think that this is the right time and for the liquid cooling to actually really become mainstream? Because every time it seems that it's going to be next year or 2 years down the road, and then something else happened. They increase the average temperature inside the white space, or they increase the efficiency of the air cooling. That's something always that. But now it really looks that we are kind of, it's really around the corner. Why do you think is the case?
I can answer that question.
Go ahead, Bruce.
I'd be happy to. Thank you.
Okay.
You know, the old water-cooled systems that IBM used to create were mainframe computers. They were very large. They were very energy intensive. They had a lot of heat in the same rack, in the same cabinet. As we progressed into modern eras of computing, we replaced those big mainframe computers with small servers that gave the operators more flexibility to utilize them the way that they wanted to program them independently and put them together in racks so that they could work together. That created a completely different environment where we had smaller heat loads in the racks, and then commercial air conditioning systems were very suitable for that. You could just blow air into the space and take it back out and sort of create a homogeneous environment with the same temperature everywhere, and sort of heat your data center like people cool their swimming pools now. And it was horribly inefficient. Thank goodness we found a better way. But it really took hotter heat loads to get us to the point to where we need to go back to the old ways by necessity. Now the racks are so hot and so energy intensive that it's going to take something that's much more aggressive than an air conditioner blowing air into the space to get the heat out of the room. And the best answer is, well, to go back where we came from and take water right to the chip. And that's what our current systems are doing. They're taking water to the chip or to a rear door heat exchanger behind the chip to remove all of that heat with a liquid. And the liquids are much more suitable, as Dale was explaining, for removing heat. They're extremely much more efficient. And we're beginning to see the hyperscale data center operators and the larger co-location operators who want to house hyperscale operations. They're beginning to move into large areas of water-cooled systems, and it's really changing the data center space from a design perspective.
So, I mean, I think we agree that density is the driver. And, we're often asked, well, what's the dividing point? I mean, how dense does the rack have to be to go to liquid cooling? And we all have our ideas, and we all thought we had our ideas. And then, it's amazing that the inertia that air cooling has, that, we'll continue to figure out new ways to cool with air, even though it's a lousy way to do it. So,
don't put water in my computer. That's a problem.
Right. So when it's going to occur or what the density has to be is hard to say, but clearly density is the driver. And I think actually once we've adopted liquid cooling, we're going to tend to cool everything with liquid. We may use different techniques, like we may say use a rear door in a less dense situation. And we'll talk a little bit about that later.
Actually, the both of you mentioned something that I think is key here, because let's say people that are not very familiar with what we're talking about, they think that it's either liquid cooled or is not liquid cooled. What most likely there's going to be a transition where part of the data center is going to be liquid cooled and part of the data they will coexist for a period of time. But Bruce, you mentioned something else that I think it's important, that the infrastructure is built to accommodate this transition. What challenges does this entail in the current status quo?
Transition from air cooling to water cooling is a completely different philosophy, and it'll change the way we operate and the way that we manage our space entirely. In fact, a new data center, if we were to build a new data center from scratch that had liquid cooling and only liquid cooling in it, it would only take about 2/3 of the floor space to house the same amount of technology and supporting systems that it does for air-cooled systems. So you can certainly save a lot of real estate that way. You can save a lot of energy that way too, because PUEs will drop dramatically with all water-cooled systems, even though we've been very successful with air-cooled systems to get them down to about 1.1. The liquid-cooled systems will do better. And of course, 1.1 means you're only spending 10% of your IT heat load in terms of energy anyway to remove that heat load, and we're very, very efficient already. But even the efficiency is only secondary to the demand to just get the heat out of the building. And with very hot computers, we need to do that. And Dale kind of challenged us with, how hot does it have to be before we need to go to liquid cooling? And that limitation has historically been about 20 kW per rack. And once you get over 20 kW per rack, then you've got to use a different form of cooling. However, like you said, we'll do anything we can to stay here and not change. And there are some new approaches that might challenge that number. And I'll invite you to pick up that conversation from here, Dale.
Well, I was going to say that it's quite common to have data centers that are both liquid and air cooled in the same system. I mean, for example, cold plate technology, especially if we want to use warm water temperatures, oftentimes only does a fraction of the cooling, and the remaining fraction has to be cooled by air. And what's interesting is that the sensitivity of data centers or IT equipment to both temperature, humidity, all air quality factors has really come a long way. I mean, back in the early days, we had to control our data centers to precise environmental conditions. But today's computers are much more robust. They can operate over a wide range of conditions. Just think about all the computers in your car and the extreme environmental conditions those computers operate at. So the ability to operate our IT equipment at wider environmental ranges, we're seeing a lot more use of outside air, and even outside air without compressor backup. So whatever the temperature is outside, say in Phoenix, Arizona, that's what we're cooling with, or maybe with some evaporative assist. But in any event, the combination of liquid cooling and outside air cooling is quite prevalent. And not only is it done just for good technical reasons, but also it's a backup. I mean, if something should go wrong with either one of the systems, you've got the other system that kind of keeps you in business. So you might be operating at a higher temperature than you want, but you'll be operating in the ASHRAE allowable range rather than in the recommended range.
Well, so much for air cooling. Now you've given us every reason in the world to stay where we are, Dale, and now we've got to move on and insist that even though it's possible and we can do this very economically, those computer manufacturers are just going to continue to push and make those computers hotter and hotter until they just can't stand having air around them at all. They're going to have to be immersed entirely to get the heat off. And I think what we're talking about is 100 and 200 kW racks, and air just isn't going to manage that.
It's not going to do it.
Now, and we're going there. I mean, the big hyperscalers are using pretty dense environments right now. We're getting up to way over 20 kW per rack, and I won't say how high necessarily, but I do know that some of the big internet companies are using what are effectively supercomputers. And they're getting to be so hot that they do need, and these are computers for artificial intelligence. They're computers for gaming. They're computers that are, driving those processors, the central processors, very, very hard. And they're surrounded usually by graphics processors that add to the heat of the unit. And 100 and 200 kW is a good target for them to be at in the near future. We can only deal with that kind of heat load, I think, by looking back into history to see who's been doing this already for many years. And that is effectively the United States Department of Energy. And their research and development laboratories, their supercomputing facilities have been doing this for years. And historically, they've used a mix of liquid cooling and air cooling in the same environment to accomplish that. And rear door heat exchangers was a very popular form of heat removal in the high performance computing space. And it's a good model for the current co-location and hyperscale and even enterprise data center computing spaces to follow. On the other hand, as we move forward, we're challenging it more and more by taking water right into the rack and taking water to the chip and through a heat exchanger inside that space, removing the heat from the chips. And in some cases, adding a rear door heat exchanger at the same time to remove the remainder of the heat from the rack that comes off of the remainder of the electronics. So we have excellent solutions already. Now, one of the more newer ones and more controversial solutions is the use of or the immersion of electronics into a liquid pool of dielectric fluids. and dielectric means that it is not conductive. Of course, if you did that with water, it would immediately implode, explode, or whatever else, and fry itself in the water. But dielectric fluids are non-conductive and don't allow for that that movement of electricity through the fluid to another metal part that is so damaging. And you can just run the fluid right over it and take it out and cool it that way. And that's a very effective and interesting solution. It's more like the human brain. And for years here in Silicon Valley, groups that I've been with, including the Critical Facilities Roundtable that Dale was so involved with for many years, used to say, well, after all, what are computers? They're simply our best effort to try to recreate the human brain. And if in fact we follow our own model here, then one of these days, I think dielectric fluids will find its way into the computing world and be a very, very important solution. Initially, anyway, it'll probably be around the edge computing applications where we have a few servers at a small place in a commercial building or something like that. But who knows where it might take us many years in the future.
That's awesome.
Yeah, well, thanks for bringing up the DOE labs, Bruce. And I was going to mention that our newest supercomputer center that Arup designed the mechanical systems, it had to be designed for both air and liquid, because at the time the design was done, our computing folks didn't know which direction it was going to go, and they didn't want to limit the bidders that would be supplying us our supercomputers. But ever since the first machine was installed, it's been real clear that we're going entirely liquid. And in fact,
so you made us design the darn thing so that it could be retrofitted to take water to the chip instead of just the rear door heat exchangers, right?
Yeah. Oh, yeah. And I think another important point is that it was designed not only for liquid cooling, but we're insisting that the computers be cooled with warm water, which means a compressorless based cooling system. So our data center it doesn't have a chiller. We use cooling towers and evaporation to cool the water that then in turn cools the computers, and bidders, or vendors that are supplying the supercomputer, not only to LBL, but a lot of the other national labs as well, are being required to accept a warmer and warmer temperature.
You are, and it gives you a better PUE that way too.
Absolutely.
And it just takes the cooperation of the technology companies and their computer manufacturing divisions to have us raise the allowable temperatures as they can operate more and more until, you can take just about any, water you want to heat it, to cool it with. It could be 100-degree boiling water. That's not boiling, but
100 degrees C. It's 100 degrees C. We could boil water, but yeah. And I think another important point there, Bruce, is that as that temperature goes up, the need for the evaporation goes down. In other words, some of our colleagues at NREL and Sandia, sorry.
Well, anyway, part of the objectives of new technologies and us trying to keep up with them is to save water as well as save energy. So the more advanced, the higher temperatures we can operate at, the less water we will need to remove the heat.
See, now I tried to have a nice pause and Bruce jumped in.
I learned that.
It's okay. It makes it interesting. Keep the conversation going.
I learned that from my friends at Lawrence Berkeley, right?
So the point that I wanted to make was that as the temperature goes up, we can actually cool the water just with air and not require the water consumption that the cooling towers create. So I think that's a big deal down the line, is if we can get higher and higher temperatures, which we are, the need for water is going to go down as well as the need for electricity.
And you can regen that heat.
Go ahead.
And
I was going to say that if we get into much higher temperatures, we'll be able to use the exhaust flow of water off of the servers to be used in industrial and commercial hot water applications, and we can just send that off for district heating and for process heating, and it will instead of being the data centers, the data center community being the enemy of the energy guards of the world, will be heroes for contributing things back to the community like we should be in the first place. And being a good neighbor and taking care of the data and giving something back.
Yeah.
So the supercomputers are very homogeneous environment. I mean, so there's a lot of control of the design. Similarly, I think, Bruce, you mentioned the hyperscalers, and they buy thousands, if not millions, of servers, and they have a lot of control over the design. But a lot of us have more legacy or enterprise data centers that are a mishmash of all different vendors and generations, et cetera, et cetera. And I think that there's certainly an opportunity for liquid cooling in those centers as well. And so like LBL, besides having a supercomputer center, we have those types of centers. And for our legacy data centers, the trend is also towards higher density. We're still doing science. We're doing what they call clusters, which by yesterday's standards are supercomputers. By today's standards, they're slow and low power, but they're much more powerful than we've had in the past, and they're dense. So even though it's a legacy data center, and even though the racks look like they did 10 years ago, the density is going up, and we're running out of the ability to cool it with air. So we have a master plan where we've developed zones in that data center for different temperatures, and so there'll be some area, or an area that's traditionally cooled, then another area that uses passive and then active rear doors, and then a third area that would have on-chip or immersion cooling. And the cool thing is there's a potential for cascading. In other words, the effluent from one zone can actually be the input temperature of water to the next zone. So you can basically get double use or triple use of the warm water.
That's very interesting. Yes.
And the whole thing is based on the premise of little or no compressor-based air conditioning. But the key is a key requirement is to have a water loop to the data center, because a lot of our buildings where data centers are embedded in an existing building, they have chilled water, and you lose the benefit of warm water cooling if you satisfy it with chilled water. So you really need a separate loop that can run to either a dry cooler or a cooling tower system
or to a heating system for the building next door.
Yeah. Yep. So you can even start with crack units. You can start with
talking about from the Department of Energy.
Wait. You are talking one over the other, so it's hard to understand.
Go
ahead, Bruce.
I was just going to say, the model you're talking about coming out of the Department of Energy and the very high densities that you've been working with there for many years is a model that the computer manufacturers and technology companies are now following, and it's very ordinary to have some of these big technology companies, and I won't name any of them specifically, but they'll send you an entire rack of their servers together, and they might be 30 kW per rack, and that just doesn't fit into most companies' enterprise data centers. And all of a sudden they've got a problem of what are we going to do with this? And it takes water cooling to get that kind of heat out of there, or breaking down the rack and taking some of those servers out of there and putting them in the rack next to it and reconnecting everything. And once that philosophy becomes dominant in the enterprise data center or the enterprise computing world, then so will water to the rack and water cooling and liquid cooling become dominant as well. I'm sorry, go ahead. Now that I've changed your mind so much, you don't remember what you were saying.
I can't agree with more.
No, that's what you get when you have so much experience in a call.
Well, we're, co-location operators have got to keep their eyes open for that as well, because when they're housing other people's technologies, and if somebody wants to bring in a rack or a few racks like that into their space, the co-location operators will be challenged immediately to take care of that load with something other than air. So we're designing the newer co-location data centers with some future proofing, so that water systems are easy to come in and into the space. We can do that by putting little points on them or connections on the piping systems if we have a raised floor environment, for example, and that are easy to connect to the current existing piping and run out a little bit of water to a rear door heat exchanger or something like that. But if we get into more sophisticated systems where they've got systems that are so hot you need to take water right to the server and right to the processors, then we're going to have to start introducing CDUs, or cooling distribution units. And those CDUs will, are coming out now, so that you can effectively just take out a computer room air conditioner, a CRAW, and replace it with a CDU right in the same spot. Hook it up to the same water connections and have the heat exchanger in the CDU ready to start shipping off a different grade of water to the computers, and set yourself up that way. So there are solutions that are available to future-proof your data center if you're willing to be a little bit flexible in the way things are designed and spend a little bit more money up front. You'll really extend the life of your, or life expectancy of your data center.
But Bruce, the beauty of that concept is once you've got that warm water loop or tower cooled water loop, a data center operator in a colo that is old school and wants a crack unit, they can put in a water fed crack unit. It works great, right? So you can once you have that loop, all the options are available. You can use a crack unit, you can use a warm water CRAW, in-row, all those options are available. But the key is you need that warm water loop.
And Bruce, we were on a call with Dale as well at the OCP, and there was a kind of a conversation whether you would put the CDU in the white space or outside the white space. There's of course pros and cons in both cases, but in your future proofing, let's say design, do you have the CDU in the white space?
Oh yeah, we put CDUs in the white space. And they can fit outside as well, but it just depends upon what kind of volume you're talking about. If you want a CDU to feed a specific area, then inside the data center is the right place to put it. If you want a CDU that feeds the entire facility, then outside would be just fine. And in fact, if these DOE guys weren't so picky about the water that went into their servers, we wouldn't need CDUs at all. But we don't want to run into any trouble with with rusting out your heat exchangers.
Okay, we are running. It's a super interesting conversation. But Christy, I think you have a question about the OCP.
Yeah, actually, I was just going to say that was a good intro to Dale. You are part of the Open Commute project, which AlphaVal is also. Can you briefly explain to everybody what are the main goals of the organization?
Well, I'm going to more speak for myself than OCP,
okay.
but a lack of standards is a major impediment to the wide and rapid adoption of liquid cooling. While most liquid cooling solutions are proprietary, most of us owners and operators want a multi-vendor solution. So the OCP is going to help us get to that point. We want, and they want, the operators want liquid cooled racks that can be reused when the servers are refreshed. For example, you'll unplug a Hewlett Packard server and plug in a Dell server into the same infrastructure, just like you do now with your electrical system. So I think there's a big need for standards, and the OCP is a really good place to promulgate those. Our supercomputers are a little different. They're sold as an entire homogeneous system, and when they're replaced, we go down to the raised floor. But in other environments like our legacy center, we want to be able to reuse that infrastructure. And there was a lack of standards.
Well, OCP's got a tremendous platform and really has been supportive of the data center community over the last 15 years or so, and we appreciate the openness they've brought. They're offering, they're bringing us together with solutions that'll work for everyone. There can't be anything wrong with that, from racks all the way to computers and everything in between. So it's outstanding organization. Dale and I are both also associated with the Energy Efficient High Performance Computing Group, which is a Department of Energy organization that's led by Lawrence Livermore right now, and yourselves at Lawrence Berkeley, that has really made some tremendous progress in this area as well, and have provided leadership to ASHRAE and ASHRAE's TC 9.9 committee to help them move into the world of liquid cooling and set the right standards and set the right objectives for the direction that they're providing to the rest of the data center community for liquid cooling. So
Yeah.
EEHPCWC and OCP and ASHRAE are all terrific organizations to become a part of and get involved with, and easy to find your way into. So look around and find a way to contribute and learn from these organizations. They're tremendous groups.
Yeah, Bruce, let me elaborate on that just a bit. Because every machine that we were getting, and typically our supercomputer centers have more than one machine running at a time. So every machine would have a different inlet temperature requirement, set by the manufacturer. So whichever machine in our data center, cut the most corners relative to their heat exchanger surface area and their thermal engineering, that drove the requirement for our entire data center. And we had a situation where we actually had to send chilled water to the data center because there was a liquid cooled computer that actually required chilled water. Now we did our best to improve the situation. Again, we cascaded. So we took the output of that computer and used it as the input to other computers. But the point was it wasn't efficient. So the EEHPC working group, or Energy Efficient High Performance Computing Working Group, got together, as Bruce mentioned, generally with most of the labs, but also the vendors, and we established standards for the supply water temperature. Not one standard, because different situations require different answers. But if you say, okay, this data center is going to be W3, everybody knows what the supply water temperature is going to be, and our vendors are providing computers that meet those requirements, and it's much easier to deal with. So we basically established the W, or created the W classifications, and then ASHRAE adopted them, and they're promulgating those standards. So the various organizations are working together. I mean, we kind of collaborated to come up with the numbers, and then ASHRAE is in a much better position to promulgate those internationally.
And if you're not familiar with the W classification of the ASHRAE, you can Google them, and you find essentially there are class of temperatures for data centers that they are supposed to work at those temperatures. So again, you can Google W classification of ASHRAE, and you find them easily. The 5 or 6 classes, right? I don't remember. Yeah.
A very important point to remember about that, though, is that as you see these standards, you shouldn't look at them as something new. They are based upon standards that have been developed and proven over decades of operating history and hundreds of data centers all over the country and the world, and do date back to the old mainframes of before Dale was a child.
I want to just add one thing to this discussion, and that's that when we were doing this, we did not have the entire cooperation of the vendors. I mean, there was a lot of pushback saying, oh, we can't do that. We can't cool our computers with warm water. Fortunately, there was a couple that said, yeah, we can do that. And that really helped, because then we could establish the standards, and now they all do it. Nobody's saying, oh, we can't do that.
No, even the chiller manufacturers are doing that now. They're going to do they're doing hot water too, and it's saving their lives, because pretty soon we're not going to need them anymore, and they're going to be looking for something else to do.
So the point is that I think the industry is responsive to their customers' requirements and needs, and it's just up to the customers to state what that is. Is to demand it, because when the customers say this is what we want, I find the industry to be agile and flexible and willing to provide what we want, and we just have to ask.
I actually have a follow-up question about this, because which is it's a personal curiosity, let me put it this way. So, but we are part of these organizations, and it seems to me that, of course, the US is by far leading the efforts. Europe, it's participating somehow. What I don't see, actually, it's Asia. And I wonder if they are doing their own things, and we are not collaborating that much. This is my impression, or you have a different opinion about that.
Well, we've been working with China with supercomputing for many years, and exchanged technology back and forth, and have a little competition going on here about who can develop the fastest computer. I promise you that there are other major computing powers in that in that area over there that are also building 100 megawatt plus hyperscale tier 4 high performance computing data centers as well. So it's not Europe and the Americas only that are sharing this, but
no,
Asia,
sorry,
got some tremendous.
I didn't make myself clear. I was not questioning that they were actually a technological advance, but there is this kind of effort to standardize as much as possible the many aspects of the data centers, and my impression is that the US is leading this effort. Europe is tagging along somehow, but in this effort of standardization, I don't see a lot of contributing from China.
Yeah, I understand.
Yeah.
I understand.
So
I think that
that's such a rich question.
Europe may be passing us up a little bit, in fact, with standardization. Go ahead, Dale.
Yeah, I mean, that's a really rich question relative to standards, because I do work both in India and China, and in the US, obviously. And we've had focus groups in those two countries where we talked about, well, what can our governments do collaboratively to help industry become more efficient? And multiple focus groups would say develop standards, but government standards. And if we suggested that in the US, we would be run out of the room. I mean, the US industry is not supportive of government standards, but in India, they are very supportive of it. Same with China. And China's built on standards.
Wow, yeah.
So that's a solution for them. So our standards work actually started in a partnership between the US and China. And we had Baidu, Tencent, and Alibaba, the big players, along with Google, Microsoft, Facebook, and Intel here in the US, to work on standards, because the Chinese were developing a competing standard to OCP. They were different dimensions, et cetera. So our goal was to try to bring the standards making people together and say, well, let's not have a China standard and a US standard, let's have an international standard. So there is interest. I think, I'm a little bit more familiar right now with India. India's data centers are probably less dense right now. They're probably on par in terms of efficiency with ours. I mean, PUEs of 1.6 to 1.8, but they lack the exemplary ones. They're putting water in data centers, using outside air. I mean, all the things we're doing quite a bit in. There's a lot of reluctance in India, but it's coming. I mean, it's amazing how things are changing. And it's an international market. So, when we're in India, we're working with NetApps and Intel and Dell, and they all have major facilities, R&D facilities, as well as production and office facilities. So the point is that they're a little bit behind, and maybe with the help of their government and standards, we'll get them where they'll be a fast learners and catch up soon. I'm pretty sure.
And in fact, they do share their information with us, and we do share their information with them. If you go to an OCP conference, you'll find that the big Asian companies like Alibaba and Tencent and like Dale was saying are there making presentations about how they have implemented cooling in their data centers, liquid cooling and microgrids, and many of the new drivers in the American data center industry are occurring in parallel in Asia as well as in Europe. And and they might take off in their own direction a little bit with standards, but we all come together again, and everything or all the standards in the world, I think, have fundamentally come out of the American professional standards organizations. And now that the rest of the world is caught up, they've developed their own standards that are built upon the same foundation, but are a little bit different all over the place. And that's something we're going to have to live with. Maybe we'll have to catch up with a few of the standards from elsewhere.
So one of the issues that you hear from Asia that have much more severe climates, I'm thinking of like Singapore, and then places like Mumbai and stuff, and they'll go, oh well, that those technologies, say free cooling as an example, that's fine for you guys in Berkeley or Golden, Colorado or something like that, but we can't do that here. Well, they are doing it there. I mean, they're building compressorless data centers in Singapore, and we're building compressorless data centers in Phoenix, which is just as severe as Mumbai and Singapore, in my opinion, in terms of, you know, high temperature, high humidity during a monsoon, and the terrible dust and sandstorms that they have are, you know, contribute to equally as bad air quality to
I think yeah, the real key issue here is that it really is in the technology where the opportunity for saving energy and having more compute power available to us really lies. It's not in the facilities design so much, but in the technology. And that technology, and the rest of us will just sort of follow suit as they get hotter and hotter and become more and more flexible. We'll just, you know, reduce our infrastructure that supports it, both on the electrical side and maybe not on the electrical side so much, but on the cooling side very much. Reduce that infrastructure and just let those computer servers run and run and run.
So I did want to mention, you know, in terms of other issues, we've thrown out a couple of times today PUE and given examples of PUE, and I'm a big believer in PUE, but there's no metric that's perfect. But as we get involved in liquid cooling, the PUE metric becomes a little bit less valid because there's a lot of equipment that crosses over between inside the box and outside the box. I'll give you one example. In immersion cooling, and even in some cold plate technologies, you eliminate the fan in the IT. Well, what that's going to do is it's going to actually increase your PUE, which is bad because you've reduced your IT energy use, and that makes the ratio worse, where in fact you've made the system much more efficient by eliminating a fan. So
what you're talking about is one of the fundamental flaws in the definition of PUE, when you've got facilities functions inside the server that are adding to the efficiency numbers.
Yeah.
So we have a hard time getting many data centers to install adequate measurement devices just to measure simple PUE. But what we would really like is to be able to separate the fans and the power supplies and other types of infrastructure other than compute and call that part of the facility or the infrastructure. And that would be a much better metric, but measuring that metric is much more challenging. But as we get more involved in liquid cooling, where there might not be fans, and then also the whole CDU thing gets a little bit complicated because sometimes people are including the CDU in the IT load. And in fact, we've seen, you know, very large fans. I mean, 5-7 horsepower fans in the computer because of the pressure drops through the computer and the coils and that sort of thing was all part of the IT equipment. So the PUE looked great, but you know, and some of the best systems pull the power supplies out, pull the fans out. They use larger, more efficient fans and power supplies. And now what they've done is they've transferred part of the calculation to the facility side, making the PUE look worse. So there are some faults, and liquid cooling really brings some of those to light.
But there is.
They figure out how to move around the variables in the equation so that it, you know, makes them look as good as possible. And then they get paid for it, and then they get a raise, and don't need me anymore. So.
But there is, I agree with you, Dale. There is a trend toward more, let's say, reliable metrics. Like for instance, now there's the concept of total cost of ownership instead of cost of equipment, which I think is very smart. Instead of looking at how much did this pen cost to buy, let me see how much it's going to cost for the 10 years going to use this pen.
Sure.
But
yeah, I think the industry has used TCO for quite some time, but it's where they draw the box. And a lot of times they'll draw the box just around the IT equipment, and that's a 3-year life or a 4-year life. Whereas now with liquid cooling, you know, that box between the infrastructure and the compute is different. And a lot of that infrastructure, like I'm talking about, we want it to last several cycles of refresh.
Exactly. I mean, for us, that there are vendors of equipment that is supposed to last 15, 20 years.
Yeah.
The total cost of ownership. It actually makes a lot of sense, because if you sell if you sell a high quality piece of equipment that's close to last 15 years, but it's a little more expensive at the beginning, if you look at the TCO, you are much more favorable, considered. Yeah. So.
Yeah, well, the key is the TCO has to be over, 15, 20, 30-year life rather than the life of that generation of IT equipment.
Yes,
right.
yes.
And there are other solutions we should be talking about as well, and that is liquid cooling as the heat rejection system, and that means using water that's available to us to remove the heat instead of air. And if we can use that, then we can get rid of all of the chillers and the cooling towers and all of that heavy-duty mechanical equipment that's so energy intensive and so polluting, and just use our natural waterways to cool our gas. And of course, the environmental community will have a problem with that if we park them too close to their frogs, or exactly. In the way of their motorboats.
Something to say about that. Yeah, they have something to say about that.
But it's a very interesting concept, and of course, we've all heard about the underwater data centers that one of the hyperscaler operators is operating and working with, in the floating data center here in the Bay Area. And it's just a model that's very, very valuable and should be pursued, I think. And not only does it save an awful lot of energy and allow for much higher heat loads, but it also provides for the opportunity to move a data center right into town where the utility would tell you, you can't have any of my power. There's no power here for you to come in here and get 10 megawatts in any of these buildings. But if you drive into the port, they almost always have 10 megawatts of power to sell you, and usually at a lower rate. So I think it's an interesting concept.
So thanks to our guests, Bruce and Dale, for this very interesting and educational conversation. As usual, if you have any questions, you can find us on LinkedIn. Again, I am Christy Smith.
And I'm Cosimo Pecchioli. And stay tuned, because in the next episodes, we will talk about adiabatic cooling with one of the vendor. And then we will actually interview one of the major integrator for cooling skids for data centers in the US. And then we will have much more in the pipeline for new podcasts. Again, as Christy said, if you have any question, you can find us on LinkedIn or, of course, alflaval.com. And if you have any suggestion of topics that you would like to discuss in future podcasts, please let us know. Thank you very much.
Thank you.